Good evening, sir.
Ma'am.
Yeah, sir, you can start, sir.
Okay, ma'am. Okay. Good evening, students. In this class, we are going to start with the resistor and the capacitor in series AC circuit. Okay. So last class we finished with LC circuit, that is RL circuit. Sorry. Last class we finished RL circuit, and in this class we will be doing resistor and capacitor in series circuit, that is RC circuit. I will be sharing the whiteboard with you. So resistor and capacitor in series. circuit. That is called RC circuit. Now I will be drawing the circuit here. Here you have the resistance. Okay. This is the resistance. Your capacitor is here. This is your capacitor. And of course, the AC signal is given as input here. So that is shown like this, as usual. So this signal is E equal to E naught sine omega t. So here, the potential drop across the resistance. Okay, the potential drop across the resistance is given by VR, V suffix R is equal to R into I naught. R into I naught. And across the capacitance, it is V suffix C is equal to XC into I naught. Okay, so here XC into I naught. So this is the RC circuit. You have the resistance and the capacitor here, and the AC signal is fed here. Okay. So the potential drop across the resistance is VR equal to R into I naught. Potential drop across the capacitance is VC equal to XC into I naught. And since both resistor and the capacitor are in series, okay, so the current through both the elements will be same at every instance, and obviously we have these two potential drops, VC equal to XC into I naught. Okay, VC equal to XC into I naught. So XC is nothing but capacitive reactance. VR is equal to I naught into R. So here we are going to draw the phasor diagram now. How the phasor diagram looks like. So actually it looks like this. The VR, okay, that is the potential drop across the resistance VR. It is in phase with I naught. Okay, it is in phase with I naught. So here you can represent the I naught like this. So I naught is here, and your potential drop is here. VR is in phase with I naught. Okay, but here your VC, okay, your VC actually lags behind I naught by 90 degree. So VC is shown along the negative y axis. Okay, since it is lagging behind the current by 90 degree, so we are actually showing it here. Now, what is the resultant of both these things. So resultant can be shown like this. So I'm going to show the resultant like this. This is the resultant. This is the phasor diagram, and this is the resultant. Here I am marking the point P, and here I am marking the point S, and here you have the point O. So here the vector OP, okay, from O to P, the vector shows VR, which is in phase with I0, and the vector OQ, okay, OQ. So this line. So the vector OQ actually represents VC, which lags behind I0 by pi by 2. Okay, I0 is here and VC is here. Obviously, it is pi by 2. Okay, so the resultant OS, it makes an angle pi with the x-axis. So here in the phasor diagram, you will be having pi. Now we have to calculate the resultant OS. How we are going to calculate that? So now I will be writing those equations. VR squared, okay, plus VC squared is equal to E0 squared. So E0 is nothing but square root of VR squared. Okay, VR squared plus VC squared. So this is E0, that is represented by this resultant. Okay, E0 is over here. Okay, E0. So E0 equal to root of VR squared plus VC squared. And from the expressions for VC and VR, we can actually simplify this equation. So E0 is equal to square root of VR squared is I0 squared R squared plus VC squared is I0 squared XC squared. So here you can take I0 squared as common, and when you apply square root to I0 squared, you will be getting I0. So I0 into root of R squared plus XC squared. This is E0. Okay, E0 equal to square root of I0 into square E0 equal to I0 into square root of R squared plus XC squared. So here, if you want to find out I0 from this equation, your I0 will be E0 divided by square root of R squared plus XC squared, where XC is the capacitive reactance. And this phase angle tan phi, how we can calculate this phase angle tan phi? So tan phi can be calculated by VC by VR. That is obvious from this right angle. So this phi, tan phi is equal to VC, opposite side, this SP divided by OP. So that will be VC divided by VR. So VC is nothing but, you know very well, XC I0 divided by VR is I0 into R. So tan phi will be, tan phi is equal to XC by R. So here XC, okay. So tan phi, XC is nothing but 1 by omega C. That we have discussed already. When you have a capacitor in AC, in an AC circuit, the capacitive reactance XC is given by 1 by omega C. So that thing we have already discussed. So tan phi equal to 1 by omega c whole divided by r. And now, if you want phi from this equation, what you can do? If you want phi from this equation, you can actually take tan inverse. Okay, so phi equal to tan inverse 1 by omega c into r. This is the equation for phi. So these are the concepts related to this RC circuit. And now we will be finding out the capacitive impedance. Okay, capacitive impedance. Impedance means the total resistance in the circuit. Here, the resistance is due to the normal resistor R and the capacitance also. So, capacitive impedance we need to find out. So, here it is represented by Z. Okay, capacitive impedance. So, what is meant by capacitive impedance? It is nothing but opposition offered to the AC circuit. AC signals by the combination of resistance and capacitance. So that is given by ZC is equal to E naught divided by I naught. Okay. So here I naught we know very well, and of course I naught equal to E naught divided by. So I naught is equal to E naught divided by square root of r squared plus xc squared. Just now we have discussed, and from this, if we want to find E naught by I naught, so E naught by I naught will be root of r squared plus xc squared. So here, what is the value of E naught by I naught? That is ZC, capacitive impedance, square root of r squared plus xc squared. So here xc we know very well. So xc is nothing but 1 by omega c. So using this, we can find out ZC is equal to square root of r squared plus, I am actually doing it from this equation. Okay, instead of xc, we have to substitute 1 by omega c the whole square. So this is 1 by omega c the whole square. So we know very well omega equal to 2 pi f. So in that case, what will happen to ZC? So ZC is equal to now root of r squared plus 1 by 2 pi f into c the whole square. Okay, ZC equal to square root of r squared plus 1 by 2 pi f c the whole square. So this is the expression for that capacitive impedance. And now I will be discussing something about the impedance triangle. So that's a simple concept. So impedance triangle. So this is also very simple. So you draw a graph like this. And here you will be having that impedance represented like this. So here you have O, and this is phi, and this is P, and this is Q, this is S. So this line actually is the impedance, capacitive impedance Z. Okay. So these are the concepts for RC circuit, resistor and capacitor in series. Okay. Now we are moving on to the next circuit, that is LC series circuit. LC series circuit. We are going to discuss that now. LC series circuit. That means you have only inductor coil and capacitor. So let me draw the circuit now. So the inductor coil is represented by this symbol. Okay, you know very well. So this is L. The capacitance is represented by this symbol. This is C. So the AC signal is provided here. So this is E. Okay. Now the potential drop across this inductor coil is VL. Potential drop, and across this capacitor it is VC. Okay. And here you have both inductor coil and capacitance. Okay. So the current and that VL and VC. Okay, that will have a phase difference of 90 degree. So if you want to represent that in a phasor diagram, what you will do? So you have to draw the phasor diagram like this, because both inductor coil and capacitor are present. So your current is represented along this x-axis. Okay. So here you have VL on the positive y-axis and VC on the negative y-axis. So this means the current along this x-axis, it is leading. Okay, it is leading by 90 degree with respect to VC, but it is lagging by 90 degree with respect to VL. And the difference in the voltages, can be represented by VL minus VC. Okay, so here the difference in voltage, VL minus VC, because this VL and VC are in opposite directions. So the difference in these voltages can be represented by this VL minus VC. Here, how can we write the equation for the applied voltage? The applied voltage E naught is equal to VL minus VC now. So that will be VL is nothing but I naught XL. VC is nothing but I naught XC. So this is I naught within the bracket XL minus XC. This is E naught. Okay. I naught into XL minus XC. Here we need to find out the net reactance. So the net reactance can be represented by this equation. Okay, the net reactance. that is XL minus XC. Net reactance means here you have both inductor coil and capacitance. Both will offer some resistance to the flow of AC. So what is the net resistance offered by this combination? That is XL minus XC. So XL you know very well, that is omega into capital L, minus XC is 1 by omega into capital C. So this is the expression for the total reactance X. So here there are two conditions. Okay, here we have two conditions. Let us discuss that. Condition 1. Okay, condition 1. Here you can observe from this equation, if your omega L is lesser than 1 by omega C, that means your XL is lesser than XC. That means the dominance of capacitance is more. Okay, so this means the reactance is capacitive. Because here XL is lesser than XC, that means capacitance dominates, so reactance is capacitive. And the second condition, so it is exactly the opposite scenario. Okay, so second condition, if omega L greater than omega 1 by omega C, that means your reactance is inductive. That means here inductance dominates actually. Okay, so this equation is the key here, this equation. Okay, if omega L is more, that means inductance has the dominant effect, and when 1 by omega C is more, capacitance has the dominative effect. Okay, so these are the things which you need to understand very well. And now we have to find out the expression for EMF and current. Okay, so those equations also we need to discuss. So here E equal to E naught sin omega t. There is no change in voltage, but current I is equal to I naught sin within the bracket omega t plus or minus pi by 2. So here this is I naught sin omega t plus or minus pi by 2. So from this I naught we can find out I naught is equal to E naught by XL minus XC. XL minus XC. So that means E naught divided by omega L minus 1 by omega C, like that. Okay. So these are the concepts of LC series circuit. When you have inductor coil and capacitance in the circuit, you will be getting all these equations. You need to have a good knowledge on all these equations in order to solve the numerical problems related to these AC circuits. Do you all understand these concepts, students, up to this point? Whatever we have discussed now? Do you all understand this? Any doubt you have? Students, any doubt you have? Okay. In the absence of any doubt, let us move forward to the next type of AC circuit, that is LCR circuit. LCR series circuit. Next type we are going to discuss LCR series circuit. So as the name suggests, you will be having inductor coil, capacitance and resistor. Okay, all the three elements are present here. All the three elements are present in this circuit. So that's why it is called LCR series circuit. Now I will be drawing the circuit. So here you have the resistance R. Here you have the inductor coil L. And the capacitance is here. The AC signal is provided here. That is represented by this symbol. E equal to E naught sine omega t. So here you have a resistance, inductor, capacitor, everything is connected in series. Okay. So here the current at any instant through the three elements have the same amplitude and phase, but the voltage across each element, okay, but the voltage across each element bears a different phase relationship with the current. So if you take maximum current as I naught, okay, then you will be having different potential differences across L, C and R. So what are those things? Now we will be discussing. So here you see VL is equal to, because of the inductor coil, you will be having this much of drop. And because of the capacitor, you will be having I naught into XC. And VR is equal to I naught into R. So here this VR, as you know very well, due to the presence of resistance, there won't be any phase difference between voltage and current. So this VR is in phase with I naught. Okay. So this VR is actually in phase with I naught. Okay, but this VL actually leads current by pi by 2. Okay, this VL leads current I naught by 90 degree or pi by 2. So this VC actually lags behind current. So it lags behind current by 90 degree. Okay. So now let us represent all these things in phasor diagram. So I will be drawing the phasor diagram here. So this point is taken as P, and this is O. Okay, so this point is K, this point is T, and this is Y axis, and this is X axis, and this line represents the voltage E naught. So you'll be having phi as the phase difference. So along this axis, you will be having VR and of course I naught. Okay, I naught along X axis. VR and I naught are in phase, so both these phasors are in X axis. But along the Y axis, you see, okay, you are having VL minus VC. VL minus VC along the Y axis. Okay. So here you see VC is along the negative Y axis and VL here. So VL is here. So VL along positive Y axis, VC along negative Y axis. The resultant is given by VL minus VC. Okay. So this thing we have already discussed in LC series circuit. This diagram VL minus VC. Okay, LC series circuit. Similarly, here you have resistance also additionally. So that resistance is in phase with I naught. So that is represented in X axis. Here you see this VL and VC are in opposite directions. So VL minus VC will be getting here. Okay. And here if your VL is greater than VC, you will be having this kind of equation VL minus VC. Okay. So the resultant OK, this O to K, okay, from O to K, this OK actually represents the resultant of VR and VL minus VC. So the resultant of all the three is equal to the applied EMF. So now I will be writing the expression for applied EMF. So E naught is equal to square root of VR square plus VL minus VC the whole square. So that will be I naught into square root of R square plus XL minus XC the whole square. I think I can write it again here so that it is clearly visible. Okay, I may use a different color also. So this E naught, now E naught is equal to I naught into square root of R square plus XL minus XC the whole square. So if you want to find out I naught, you have to rearrange the equation. I naught is equal to E naught divided by square root of R square plus XL minus XC the whole square. So these are the expressions or equations for E naught and I naught. Now we will be discussing the impedance. Impedance means the net opposition offered by this LCR circuit. Here you are having inductor, capacitor, and resistor. All the three elements will be giving out a net opposition. Okay, so that net opposition is called impedance of series LCR circuit. Impedance of series LCR circuit. So the net opposition is called Z. So how we can find out Z? Z is equal to Z is nothing but E naught by I naught. Okay. So E naught by I naught is equal to square root of R square plus XL minus XC the whole square. So this equation we have discussed just now. Okay, here you see when you take I naught to the other side, it will go to the denominator, and this square root of R square plus XL minus XC the whole square will go to this side, that is numerator. Okay. So E naught by I naught equal to root of R square plus XL minus XC the whole square. So this E naught by I naught is equal to Z. So Z is equal to root of R square plus this XL we know very well, that is omega L minus XC is 1 by omega C the whole square. So we know very well omega equal to 2 pi F. So the expression for Z equal to root of R square plus 2 pi F into L minus 1 by 2 pi F into C the whole square. Now we need to find out tan phi. Okay, tan phi. So tan phi is nothing but XL minus XC divided by R. How did we arrive at this equation? From this graph. Here you see tan phi. Okay, tan phi is equal to VL minus VC by VR. Actually, VL minus in this right angle triangle you can see. Okay, so tan phi equal to VL minus VC divided by VR. So that will give you XL minus XC by R. Okay. So XL you know very well, that is omega L minus XC is 1 by omega C whole divided by R. So we know very well omega equal to 2 pi F. So tan phi is equal to 2 pi F L minus 1 by 2 pi F C whole divided by R. So this is the expression for tan phi. And the reactance of LCR circuit is one more equation. Reactance means it is a very simple concept. The opposition offered collectively by inductor and capacitor, that is X equal to XL minus XC, simple. That is called reactance. Okay. Impedance means collectively due to resistor, inductor and capacitor. Okay. The opposition offered by all the three elements is called impedance. Here the opposition offered by inductor and capacitor together is called reactance, that is X. X equal to XL minus XC. So now we will be writing few more equations for this LCR series circuit. So that is called impedance triangle equation. Impedance triangle equation. So impedance triangle means you will be having one right angle triangle now. So this is XL minus XC and this is phi and this is Z and along the base it is R. So from this right angle triangle you can have these equations: z equal to root of xl minus xc the whole square plus r square. So one equation, and tan phi is equal to xl minus xc divided by r is another equation, and from this you can write cos phi also. Cos phi is nothing but adjacent side by hypotenuse, that is r by z, and sin phi also you can write. All these equations are important, students. So from these equations you will be solving numerical problems with the help of these equations. So now please observe carefully. Sin phi equal to xl minus xc divided by r. All these equations are important. So we have completed LCR circuit also. Do you all understand these concepts, students? Any doubt you have? If you have any doubt, you can ask me. Yes, students, any doubt you have? Okay. Now we are moving on to resonance conditions. Okay, we are moving on to resonance conditions. So series resonance. So what will happen at resonance? Okay, what will happen at resonance? At resonance, XL equal to XC and VL is equal to VC. That means phi is equal to 0. So what is the meaning of this? The voltage and current are in phase. Okay. All these are the equations for resonance condition. So impedance will be minimum. Okay. Impedance will be minimum. So that minimum impedance is given by R. The current will be maximum. So I max is equal to E naught by R. And of course, E naught will be equal to VR. So these are the resonance condition equations. Now we will be discussing something about the resonance frequencies. So we know very well XL equal to XC. So that means omega R L. Okay. This R is in suffix subscript. So omega R, that means resonance. L is equal to 1 by omega R into C. So that when you cross multiply this omega, you will be getting omega square R is equal to 1 by LC. So omega R will be, now when you take square root, that will be root of 1 by root of LC. And we know very well omega is nothing but 2 pi into F. So here resonance means Fr equal to 1 by root of LC. And from this resonance frequency Fr equal to 1 by 2 pi into root of LC. Okay. This is the frequency. Do you understand this, students? So now we will be discussing some more concepts related to these series resonance conditions. Variation of Z with F. Variation of that impedance. Okay. Variation of impedance. With frequency. So if F lesser than FR, that means your XL will be lesser than XC. Okay, if your frequency is lesser than the resonant frequency, that means the circuit behaves like capacitive circuit. Okay, you see the capacitive reactance is more than the inductive reactance. So circuit nature is capacitive. Circuit is capacitive. On the other hand, if your F is equal to FR at resonance frequency, then XL will be equal to XC. That means the reactance offered by inductor will be cancelled out by reactance offered by capacitance. So circuit is resistive here. Circuit is purely resistive. That means the presence of inductor and the capacitor won't have any effect. So circuit is resistive means your phi will be 0. There is no phase difference. But if your frequency is greater than resonance frequency, what will happen? Then your XL will be greater than XC. So circuit is purely inductive. Okay. Circuit is purely inductive. So here phi will be positive. In this case, phi is negative. In this case, phi is negative. So all these are important. So at resonance condition, usually the impedance of the resonance circuit is minimum. So it is called acceptor circuit. Okay. So in TV or radio sets, whenever we tune for a particular station, actually we adjust the resonance frequency. So when our resonance frequency is achieved, then the TV or radio is ready to receive the signals from particular station. Okay. So all these things are important. Then the next thing is quality factor. Okay, quality factor or Q factor. So quality factor, otherwise called Q factor. What is meant by Q factor? So Q factor is given by Q is equal to 2 pi, okay, into maximum energy stored per cycle divided by maximum energy lost per cycle. This is the formula for Q factor, and we have some more equations also for Q factor. So that is Q is equal to omega naught by omega 2 minus omega 1. That will be omega naught L by R. This is 1 by omega naught R into C. So this Q factor represents the sharpness of resonance. Okay, when you draw the graph of current with respect to frequency, so this Q factor will tell you how sharp the resonance curve is. Okay, so this Q factor is actually a unitless and dimensionless quantity, and it is merely a number. Okay, Q factor is always represented in numbers only, so you don't have to put any SI units or any other thing. Okay, just you need to put the value for the Q factor. So one more equation for this Q factor is at resonance. Okay, at resonance, your Q is given by XL at resonance frequency divided by R. So we know very well XL and the XC are equal at resonance. So the formula can be written in this way also. So this will be 2 pi FR into L divided by R. This is equal to 1 by R to root of L by C. So this is another equation for Q factor. And the next concept is magnification. So at resonance, your VL or VC is equal to QE, Q into E. Q is the quality factor or Q factor, and E is the supplied voltage. That EMF, you know very well. So it is the supplied voltage. So this is called magnification. At resonance, magnification will be equal to Q factor. Then the sharpness of the circuit. The sharpness. Sharpness is actually directly proportional. As we have discussed right now, quality factor describes the sharpness of the curve, sharpness of the peak obtained in current versus frequency graph. Sharpness is directly proportional to quality factor, and that is also directly proportional to magnification factor. So this means when your R decreases, okay, what is the meaning of this? When your R decreases, that is resistance decreases, that will lead to increase in quality factor, that is Q increases, and that means your sharpness also increases. All these things are important. Okay, do you all understand the concept, students? Whatever we have discussed up to this point, up to LCR circuits. Yes, students, LCR circuit, up to LCR circuit, do you understand? So tomorrow you will be, tomorrow evening you will be getting a question paper, okay, containing multiple choice questions in the topics whichever we have completed. up to this point in alternating current. Okay, tomorrow evening you will be getting that. So please be prepared to take the test. Okay. So revise your lessons properly, regularly. Then only you will be able to get a good command over the concepts, and you can solve the numerical problems easily. Okay. So be prepared for the test which you will be getting tomorrow. Okay. And that test will consist of questions from the alternating current on the topics whichever we have discussed up to this point. Okay. So thank you so much for joining the session. We will keep it this much for this session, and we shall continue our discussion on the topics in our next class. Thank you so much.